Yesterday we started talking about graphs of functions, and we mentioned what x-intercepts were and what y-intercepts were. So just as a review, the y-intercept is the point where x is 0 and you have a y-coordinate. And in order to find the y-intercept, you simply just plug in x equals 0. So you want to find f of 0. In the case of the x-intercepts, these are where the graph crosses the x-axis. So for each of them, the location looks like x comma 0. The y-coordinate is now 0. Now, if I have f of x equals a function, let's say x squared plus 2x, and I said that this is the location where y equals 0, well, what is y? Y really is this entire function, right? That's y, right? So y equals x squared plus 2x. So when I say y equals 0, that means this entire function is equal to 0. So in order to find the locations of the x-intercept, you set the entire function equal to 0. Now, x-intercepts then, because they're found by setting the function equal to 0, they're also called the zeros of the function. Similarly, how do you find the zeros? Well, they're the solutions of the equation, and they're also called the roots of the equation. So yesterday I mentioned that these four words, x-intercepts, solutions, zeros, or roots, all mean the same thing. Okay? So when I ask you on a test to find the roots, that's what you need to find. X-intercept, that's what you need to find. They all mean the same thing. Okay? All right, so let's take a look at this example. It says, use the graph of each function to approximate its y-intercept and zeros, then find the values algebraically. So if you look at the graph, okay, the y-intercept is where it crosses the y-axis. In this case, where does it cross the y-axis? Here, okay? So that's the y-intercept. What else could that point serve as? It could also serve as an x-intercept, right? So the y-intercept is 0. So the x-intercepts then are 0, 0. What else? What other x-intercepts are there in here? It looks like 1, 0 and negative 1, 0. All right? So this was by looking at the graph. Now, if we want to confirm algebraically, which you're going to have to do, we'll do this. For the y-intercept, we want to find f of 0. For f of 0, you plug in 0 into each of your x's here. So it's 0 minus 0. Sure enough, f of 0 is equal to 0. For the x-intercept, we want to set the function equal to 0. All right, so we say x cubed minus x is equal to 0. We now factor this. You can factor some more. X minus 1, x plus 1 equals 0. So x is 0, 1, negative 1. Okay, so I have 3 zeros. X is 0, 1, negative 1. And they're expressed either this way or in coordinate form. And I'll specify clearly. Okay? All right, let's do one more. They're written both ways. To find the x-intercept, you set the equation equal to 0. To find the y-intercept, you plug in 0 for x. Okay? Moving along, we're going to do the same thing for this graph now. The function is 2x squared minus 5x minus 3. So if you look here, it looks like this is the y-intercept, okay? So the y-intercept looks like is -3, 0. And we are going to confirm algebraically, okay?
Wait, -3, 0.
Oh, sorry, 0, -3. X is 0, y is -3. For the zeros, okay, there are two zeros here. It's the location where it crosses the x-axis, so here and here. Now, what are those points? Well, this one is easy. X is 3, y is 0. This one, it's halfway. The best approximation you can do based on how this is calibrated is you can go to the half, right? So it's -0.5, 0. Now let's confirm all this algebraically. Algebraically, to find the y-intercept, we have to plug in 0 for x. So we need to find f of 0. You need to get used to the proper terminology, right? F of 0 means the value of y when x is 0. Well, this is 2 times 0 minus 5 times 0 minus 3. F of 0 is equal to -3. Okay? Next, to find the x-intercepts, notice how it says zeros here, but I'm looking for the x-intercepts because they're synonyms. I could have also written roots or zeros, or solutions. To find the x-intercept, you set the whole function equal to 0. All right, now we're going to factor this. 2x, x, and how should we factor this one? 3 here and 1 here. This gives us 6, but we need -6 plus 1. So x is -0.5, +3. All right? So those are the two solutions. Those are the zeros. Those are the x-intercepts. At any given time, whenever you look for the solutions of an equation, you're always looking for the points it crosses the x-axis. All right? So the zeros are -0.5, 0, 3, 0. Okay? Either way. All right. Symmetry. Symmetry is a big thing in math because most of the time, functions have natural symmetry, okay? It is possible for a function to be symmetric around the axes. So look at this function, for example. If you fold this along the x-axis, the top and bottom will match perfectly. So we say this is symmetric with respect to the x-axis, okay? Now, looking closely at this function, all right? For the same value of x, suppose this is x equals 3, right? How many values of y are there for this one? How many values of y? 1, 2, okay? So if x is 3 here, there are 2 values of y. So if you go up here, suppose y is 4, what would this value be? -4. All right? And if I happen to pick another value for x, here, x equals 2, let's say. If I go up, I will have a value for y. And if I go down, I will have another value for y. And how would those two green points relate to one another? One is the positive and one is the negative of the same value. Okay? So what's the moral of the story? When something is symmetric along the x-axis, right, it has 2 values for y, one positive, one negative. Looking at it another way, okay, both +4 and -4 correspond to the same x value, right? X equals 3. So whether you have positive y or negative y, you get the same value for x, okay? Same value for x. Meaning, if you want to test algebraically for whether something is symmetric along the x-axis, the way you do that is you replace y with negative y, and you see if you're going to get the same equation back. Okay? We're going to do lots of examples. Now, in this case, this graph is symmetric with respect to the y-axis. All right? And same thing here. Now this one is reversed. For the same value of y, how many x's do I have? 2 x's. Okay? So suppose y is equal to 5. I have 2 x's that correspond to that. Oh, let's say -1 and +1. So to test for it algebraically, we replace x with -x and see if we're going to get the same function back. So for x-axis symmetry, change the y. For y-axis symmetry, change the x. Now, something can also be symmetric with respect to the origin. Look at this one. If I flip this function over, downward, and then along the y-axis, then the two ends will match, right? So this is symmetric with respect to the origin. You flip down and then over, and you have symmetry. Okay? Imagine you flip this one down and then over, you're going to have symmetry. So how do you test for this? You replace x with -x and y with -y, and you're going to see if you're going to get the same function back. All right, so let's do a couple of examples. In practicality, it's really a lot simpler than it looks here. So look at this one. The first one. You're given x equals y squared. Okay? We want to test algebraically whether this has any symmetry. So here's what I do. I separate my workspace into 3. I want to test for symmetry around the x-axis, the y-axis, and the origin. Okay, and I literally split them up like this. To test around the x-axis, I'm going to replace with -y. To test around the y-axis, I'm going to replace with -x. And here, -x and -y. What does that mean? That means here, I say, this is the original equation, right? So I say, all right, let's suppose I make y -y. So x equals -y squared. And then I simplify. When I simplify, what do I get? X equals y squared. Once you simplify, what do you notice? What you get is the original equation back. Because you got the original equation back, that means this is symmetric with respect to the x-axis. All right? So just put a check here. It's symmetric around the x-axis. Now I'm going to do the same thing for y. Yeah.
If you actually try to plug it in, though, how would you do that? Like using that equation?
Okay, so one more time. I want to test whether this equation has any symmetry. There are 3 possibilities. It could be symmetric around the x-axis, the y-axis, and the origin. For each of these, there is a test. The test for the x-axis is plug in -y and simplify. For the y-axis, you plug in -x and simplify. For this one, you plug in -x, -y, and you simplify. Now, what does it mean to plug in -y? This is the equation, right? X equals y squared. We're going to replace y with -y. Are we okay with this part? Now we simplify. When you simplify this, you get x equals -y squared is just +y squared. What happened? What did I get back? I got the same function back that I had originally. That means this passed the test and it's symmetric around the x-axis. Now let's test for the y-axis, okay? For the y-axis, we're going to replace with negative x. That means this one, x, gets replaced with negative x equals y squared. Okay? If you simplify, this is x is negative y squared. Did I get the same function back?
No.
No. So it fails the symmetry test for the y-axis. It's x equals negative y squared.
Like the same arch.
It's just flipped around. The origin now, we're going to plug in negative x and negative y. So you say negative x equals negative y squared. Okay? And now try to simplify as much as you can. Negative x equals y squared. X equals negative y squared. Did I get the original function back? No. So it fails that one too. That means this has symmetry around the x-axis only. Okay? This was done algebraically. Now, looking at the graph, can you see from the graph that this has symmetry around the x-axis? Right? This is the x-axis. If you fold this around the x-axis, it's symmetric, right?
Yeah.
So sure enough, the graph already tells you that it's symmetric around the x-axis. Okay? Symmetric with respect to x-axis. All right, this one, we're not given the equation. We're just going to look at the graph, and you see that it's symmetric around the y-axis, right? So it's symmetric with respect to the y-axis. Moving on. This one, if you flip this part, if you flip this upper part around, like to the right, and then you flip it down, this and this part will match, right? That means this is symmetric with respect to the origin. What about this one? Just symmetric around the y-axis. So that was symmetry. Now, even and odd functions. Even and odd functions have a totally different test. The test for even and odd functions is, you do the same thing each time. You look at f of negative x, okay? And there are three possibilities. So you plug in negative x, you're either going to get the same function back, the negative of the function, or something completely different. If you get the same function back, then it's even. If you get the negative back, it's odd, or we say it's neither. Let's do examples. So the test for these is always look at what f of negative x is, okay? So what is f of negative x? I'm going to plug in negative x for each of the x's. So I say negative x squared minus 4 times negative x plus 4. You simplify as much as you can. You get x squared plus 4x plus 4. Now, compare these two. Are they the same?
No.
No, they're not the same. Now, here is the other question. Then you ask yourself, did each of the terms here change signs? No, not all of them changed signs. Each changed signs. No. That means It's not even, it's not odd, it's neither. We're going to do a couple more examples. Let me do these other examples now. Look at this one. We're going to plug in f of negative x. Okay? Negative x squared minus 4. You simplify. F of negative x is x squared minus 4. Now, compare what you got with the original. How do they compare? They're the same. Means this is an even function. Okay? So you write even. Look at this next one. You plug in f of negative x. Negative x squared. Negative x to the 4 plus 1. What do we get? X squared over x to the 4 plus 1. Compare these two. Are they the same? Yes, they're the same. So what type of function is this? Even. Okay? No, it's odd if every single term has switched signs. Well, look at this one. F of negative x is 1 over negative x. Well, let's simplify. The only way really you can simplify is you can say this is the same as negative 1 over x.
That means did all the terms change then?
Right, so compare these two. Okay, this is the negative of this one. Okay, this is the negative of the original. So it's odd. Finally, the last one, f of negative x is the square root of negative x squared minus 3. The square root of x squared minus 3, what type of function? Even. All right? So at first glance, they're scary. When you look at them again, not so scary. Okay? Yes.
So you always plug in to find if it's even or not, you always plug in negative x.
Yes.
And what if only like one of the terms switches signs?
Then it's neither. All right, so do this one. I'll take questions, but I'm going to add another one. I'm going to add f to here. So do this one, please. Whoops. So check whether this is even, odd, or neither. Don't give away your answer. When we do plug in f of negative x, or when we look at f of negative x, we get negative x to the power of 3 minus 2 times negative x. So what we get is negative x cubed plus 2x. Now, compare the original with this. How do they compare? The first term switched signs. The second term switched signs, right? That means this is the negative of the original function. That means this is odd. Okay? So in order for it to be odd, each and every single term must have switched signs. All right? Mathematically, the way we write that is we say f of negative x is equal to negative f of x. Okay? Now,
So is that the final answer?
this is the final answer. It's odd.
So what will we put the f of negative x equal?
You don't have to put that part. Okay? Let's graph one of these. Let's graph e, the square root of x squared minus 3. And what better way to spend your time when you go to the beach than to draw some, write some of these functions on the sand, test for symmetry, test for even or odd, and honestly, it just makes the time fly by. So what do we have here? We have the square root of x squared minus 3. All right, whenever I'm in a graph, I don't know what my previous windows were. I instinctively just press zoom, and the sixth option is the standard zoom. So it gives you the standard viewing window. Zoom 6 gives you this. Okay, now we said that this was an even function. Okay, even functions look just like this. In an even function, both ends of the graph are either up going to positive infinity or down going to negative infinity. So even functions are also symmetric with respect to what? The y-axis. Okay? Right, so let's see. Let's graph an odd function, x cubed minus 2x. Let's graph this one. Yes. So when you're going to put in multiple functions, and you might want to come back to this and you don't want to erase it, if you go on the equal sign and click enter, it unhighlights it for you. So even though the function is there, it will not graph it. Okay? So here we're going to put in x cubed math 3 minus 2x graph. Okay? How does that look with respect to the origin? Okay, so for odd functions, what I want you to know for odd functions is one of the ends points up and the other one will point down. Okay, so an even function will look like this or like this. An odd function will look like this or like this. Okay, you can take that to your dance teacher and you can have this wonderful math dance.